Guess I'll start recording from chapter 2. Um, all right. So in chapter 2, work the practice problems. Practice makes perfect. Get you used to them. All right. Dr. Kim's video on this chapter. Plus, when I'm done, I will upload this video. Unfortunately, we're not going to have the latter part of the chapter 1. Okay. So work the problems through. All right. So we talk about measurements. Measurements is a number with a unit. Units are very important. Okay. Now, in science, we use mostly metric units, but we're going to introduce the conversion of the English units and metric units as an exercise for you. When we get down to chemical reactions, this technique that we utilize can be hopefully easily transferred to how we're going from compound A to compound B. Okay. Now, again, units are important because if we say something like a book weighs 8, well, that number 8 doesn't mean anything. It's just a number. We got to put units. Is it 8 pounds, 8 ounces, 8 kilograms, 8 grams, 8 micrograms, so on and so forth. So number without units is meaningless. Also, there's every measurement. This is something important here. Everything we measure has degrees of uncertainty. I'm sure you're familiar with this. Okay. There are balances to weigh things that we can get to the 4th decimal point, or there are balances that maybe give us plus or minus 1 gram. And so, but there's an uncertainty. The last number has a degree of uncertainty. I could take a weight, I could measure it and say 10.1 grams. Someone else could read it. No, it looks like 10.2 grams to me. They're not incorrect, nor am I. It's just because that tool that we use to measure has a degree of uncertainty. Okay. And so we're going to talk about what's called significant figures. And sometimes that could be confusing, the concept of significant figures. So we're going to spend a little time with that. With respect to length, we're going to use the units of cm, which is centimeters, mm, which is millimeters, and m, which is meters, and km, which is kilometers or kilometers. Okay. Now, we can, the instrument, I just mentioned how accurate the instrument, how accurate the instrument we have determines how accurate we can represent our data. Now, if you look at these two rulers, obviously it looks like the top ruler has less increments. And so if we needed to, let's say, take a measurement and maybe we needed to mark this spot right there. Okay. Well, we can see with the white ruler, we would say, I don't know, maybe that's 4.3 or 2. Let's assume this is millimeters here. But that same mark on the bottom ruler, we can be more accurate. Okay. That number on the white ruler, we can go maybe 4.3, 0.3. However, the one in the bottom, we could say almost 4.25. We went to the 2nd decimal place, to the hundreds. So the bottom ruler has more accuracy. So if we were to use the white ruler to make measurements and do calculations, our answers should not be more accurate to at least the 1st decimal point. Whereas if we use the brown ruler, we can go to the 2nd decimal place. Okay. And so we cannot, you know that you can do a lot of calculations in your calculator and you're going to give like 20 numbers. Well, you would never present your data with those 20 numbers on your calculator, because keep this in mind, you can't present your data more accurate than the tools of accuracy of your measurements. Okay. And so you're only good to say 4 grams. I will give my answer to one number, like plus or minus 4 grams. I could not say 4.000000, etc., because I'm not that accurate. Okay. So again, which has more uncertainty? The white one. Okay. Here's a good example of accuracy. In mass, we use the units of mg, which is milligrams, kg, which is again kilograms, and g, which is grams. The balance on the left, a lot less accurate than the balance on the right. If you were in the lab, the balance on the right is what you'll be using to measure. That one you can go to 3 decimal points. Okay, so you get a little bit accurate with the balance on the right. Now, how do we differ between mass and weight? Is there a difference? Well, yes, there is. But we're stuck on the Earth. And what happens is we kind of interchange the term mass and weight, because mass is simply a measure of all the matter on an object. Okay. Whereas weight is a function of gravitational force. So you may or may not know this, but if you went to the moon, you can weigh a lot less, approximately 1/6 less, I believe, because the gravitational forces on the moon are much less than the Earth. But the mass that you have here on Earth is the same mass that you take to the moon. Okay, so there's the difference. But here on Earth, because we're not out in space, we tend to interchange mass and weight with respect to units. Okay, so weight is a measure of the force of gravity, and mass is a measure of the amount of matter in an object. Okay, the relationship is this: weight is equal to mass times gravity. Here on Earth, it's 9.8 grams per meter square, but we're just going to keep it as when we talk about mass, we're talking about the weight. So we're going to keep the same units. We're not going to complicate it. An astronaut weighs 170 pounds here on Earth. Go to the moon, you're looking at about 29 pounds, simply because the gravitational forces. Now, with respect to volume, the units that we utilize are given down here. Capital L for liters. K is, again, kiloliters. M is for milliliters. And there's diagrams on the far right to give you an example of what we use to measure volume. Okay. All right. Now, you may be familiar with this. I'm sure there's some nursing students out there. Okay, what kind of units do most syringes have? CCs. I need 10 CCs of so and so. What that means is cubic centimeters. Okay, cubic centimeters. So it's a cube. So 1 centimeter by 1 centimeter by 1 centimeter, cubic centimeters. Okay, the conversion factor is this: 1 milliliter is equal to 1 cc. Okay, so cubic centimeters also written cm to the 3rd power. That's cubic centimeters. So if I have 1,000 cc's, I have 1,000 milliliters. We're going to possibly have some examples where we have to read a volume. What happens when most liquids, when you put them in a cylinder, they form this concave shape. Okay, we call that the meniscus. Now, the way we read that is we read the bottom of that meniscus. And so we read right in this area right there, okay? And we go to the scale. When you read this, be aware where your scale starts. Some instruments, the 0 starts in the bottom like this one. And we go from 0 to 25. And so this meniscus would be 20, and that could be 21, depending on the units. not the other way around. So be aware of where your 0 point starts. Okay. And when you read this again, read the bottom of the meniscus. I'm sure you'll see some diagrams down the road and say, hey, what is the volume of this liquid? Which brings us to the point of significant digits. Now, this is where I think the term significant kind of confuses things. When we talk about significant figures, we're talking about how accurate your measurement is. It has nothing to do with whether it's worth anything or it doesn't play a factor in the calculations. Okay. And so, for example, the bathroom scale versus the surgical scale, we know which would be more accurate. Obviously, the surgical scale would be more accurate, and which would have more significant figures, the surgical scale. Okay. The bathroom scale wouldn't have as many figures, significant figures, because it's not as accurate. Okay. Again, this example here, if we were to take that measurement there, we would have to just ballpark guess that number measurement would be 29 point, I don't know, 2. Okay. Compared to the bottom one. Okay. So the bottom one, let me, would you agree that this might be 29.2? Ballpark? Okay. This one here, 29 point from my angle to, I'm going to call it 5. Oh. Would you agree that, yeah? Okay. So notice the top measurement, we're only good 5. Well, I'm guessing, look at 5. If you look at down here at the bottom, the units are a tenth, right? From 29 to 30, every line represents a tenth. So that red line is somewhere in the middle between the 2/10 and the 3/10. So for my angle, that distance is 5. You see that, Sonia? Okay. Up here, I can't do that because I don't have enough increments between the 29 and the 30. So the best I could do is guess at the 0.2. You may see 0.3. That's okay. That is the degree of uncertainty, that last digit. And that is governed by how accurate your measurements are. The ruler on the bottom is a lot more accurate. I can go to the 100 place in my estimate. So my degree of uncertainty would be in my last digit. This would be the degree of uncertainty at the 100 place, and this would be in the top one in the 10th place. So when if I were to take that data, 29.25, I would have 4 significant figures there, okay? And they would play a factor in my calculations, okay? I could not go any more accurate than 4 digits. And it'll become clear here in a second. All right, so, let me get rid of some of this stuff here before all right. So there's some rules about significant figures. Numbers, all the whole numbers, 1 through 9, are considered significant figures, okay? So if we look at this number here, 4,895.2, it contains 5 significant figures. Okay. 5 significant figures. So all whole numbers are significant. Now, the leading zeros. Here's a number less than 1. The leading zero, 0.000, those numbers are not considered significant. All they're doing is holding our decimal place, telling us we're going 4 decimal places over to the right of the decimal point, okay? but they're not considered significant. And in this example, 5454 are whole numbers, so this number has only 4 sig figs. Now I'm going to go through all the rules, and then I'm going to break it down to ask yourself 2 simple questions to answer whether a 0, because the 0 is the one that gets people confused. Okay. Any 0 that has 2 integers in front and the back is considered significant. So the number 3050, okay, that 0 between the 3 and the 5, it's captured. We call it captive zeros. So we consider that significant. However, the 0 after the 5 is not. So it's not considered significant. So that number only has 3 significant figures. All right. The second example, 0.00, again, like rule number 2, they are leading zeros, so they don't count. 2001, those zeros are between 2 whole numbers, therefore are considered significant. Okay. So we have 4 sig figs for the second example. Now, we need to learn which ones are significant and which ones are not, because when we do a mathematical function, depending on the number, if we were going to multiply 3050 with the second example, our answer could not have more than 3 sig figs. Okay, we'll get some more examples. Trailing zeros, those are zeros after a whole number. Okay, so the first example, 0.0880 has 3 sig figs, whereas the number 28,500, there's only 3 sig figs. Okay, all right. Anytime you add a decimal point to your number, any 0 becomes significant. So the number 285.00 has 5 sig figs. In that case, those zeros are significant, which brings me to the question here that you ask yourself. Let me double check that. Okay, 2 questions. Numbers 1 through 9 are significant. That's an automatic. Zeros that are in front or are surrounded by whole numbers are significant. That's automatic. The other zeros, you may not be sure. So you ask yourself this question. Question number 1, for zeros only. Is there a decimal point anywhere in that number? Okay. If the answer is yes, that 0 becomes significant. And then second question, is there an integer in front of that 0? Okay. If the answer is yes, that 0 is significant. If the answer is no to any of those 2 questions, 0 is not significant. For example, let's do one. Let's look at this 0 right here. 0.0. You look at both of them, 0.0. First question, is there a decimal point in that number? Yes. Okay. Second question, is there an integer in front of those 2 zeros? Answer is no. Those zeros are not significant. Okay. Try, let me change my color here real quick. Try this 0 right here. Ask that question. Is there a decimal point in that number? Yes. Is there an integer in front of that 0? Yes. 2 yeses means that 0 in pink is significant. Okay. All right. Ask the same question to these zeros again. All right. Is there a decimal point in that number? Yes. Is there an integer in front of those 2 zeros? Yes. 2 yeses, they're significant. So that number has 5 sig figs. Okay. Hopefully that makes it. You cut out. Oh, okay. Okay, the question is this. Let me put that number. The number is this. 1.000. Okay, who can tell me if those zeros are significant? You can put it in the chat or you can speak out. It's okay. There's only 11 of us here, so it's supposed to be 29. And those 11, 2 of them are me. Yes, there's a one in front. Okay, how many? 4? Okay, 4 is correct. 4 is correct because you asked the question for the zeros. Is there a decimal point in front in that number? Yes. Is there an integer in front of those 3 zeros? Yes. Hence, those zeros count. I have a total of 4 sig figs. So this has 4 sig figs. Okay. All right. Let me erase all this. Okay, to answer your question, Sonia, you typed it in. All right. Now, there are exact numbers, and exact numbers are not used in any of your calculations as far as sig figs. They're exact numbers. When somebody says there's 14 people, okay, there's 14 people, and that's an exact number. 3 feet per yard, that's a conversion factor. There's exactly 3 feet in 1 yard. There's not 3.1 or 3.2 or 2.8. It's exactly 3 feet. There's 100 pennies in a dollar. Anything you count, like the 100 iPods or 12 cans of beer, those are whole numbers. So when you see whole numbers, you're not going to use them in the final calculation of your answer. Okay, they don't play a factor in sig figs. They will play a factor in the math. Don't get me wrong there. They will play a factor in the math, but they will not be in a factor in determining the final significant figures at the end. Okay, things that are measured. Anything you measured, length, mass, what did I say, and volume, have a degree of uncertainty. So if you measure something 7 inches, you had an instrument that you measured that. That would be, that is not an exact number. 200 pounds or 10 ounces, anything. The only exception is that 1 inch is equal to 2.54 centimeters. That is considered an exact. Okay. All right. Anything that measured, remember this. I'm going to finish this slide and then I see it's 3 or 4. And then we'll stop here. Anything that's measured is not exact. Okay. So they were not, excuse me. So anything that measured would be a factor in when you're calculating significant figures. All right, so let's stop it here. Unless you want me to continue, I'll be more than happy to. But now I will stop it here because I did say I'll spend an hour. I don't want to make it very. So we are on slide 16. Okay. Any questions, comments? Yeah. No questions? All right. All right. No questions. I will see you guys tomorrow. Yes, the question was there's a question about the quiz on Monday. It opens up at 8 a.m. and it shuts down at 11 p.m. Excuse me, 10 p.m. Okay, so you have that time span to take it in. Okay. Any other questions? All righty then. Thank you for showing up. Keep up with your studies. Stay safe out there. Thank you, Abigail, and you too. Okay, see you tomorrow.